Bismillahirrahmanirrahim. In the previous lecture, we were discussing about different examples of the pushdown automata. Let's see some more examples here. Let's first start with the palindrome, as palindrome is basically a sequence of words that it's same if you read from left side or if you read from the right side. In case of palindrome, we will see different types of palindrome. Some palindrome is even, some is odd. Let's solve one by one. An even palindrome and odd palindrome, and then we can push down automata that can support both even and odd. Let's see this particular example. In this case, what you did, you have a clear identifier which identified the midpoint that you have a word, then you have a character which is C, and then you have a word, the same word in the backward form. And if, for example, here this is, and it says it is static, so it might be possible we only have C. Then we may have ACA, we may have BCB, and so on. So these are the examples of, this is an example of the odd palindrome, but a type of odd palindrome where you clearly have an indication that will indicate the middle elements. So in order to create a PDA, let's first create the PDA for the smallest one. What we have here, we will first of all, in this case, when you have only C, we don't need to push anything, because we will define that if it is we need, in this case, it's not like doing A as push and B as pop. How we will define the logic? We will define the logic in the way, like for example here you have an identifier C, so everything that is before C we will do a push, everything that is after C we will do a pop. But whenever we will do popping, we will see that if we have an element, currently the one that we are reading after C, if that one and the stack top is same, then we will do what? Then we'll do the popping, otherwise we will not do the popping. So if you have only C, for C we don't need to do any sort of push. So we will be first of all here in Q0, as we have keep this Q0 for what? For pushing. So what we did here, we need to change the state, and for C, as you are in Q0, okay, the input you receive is C, on the stack top it is Z0. What you need to do is you need to move to Q1, and then you don't need to do anything, and then you just need to move. So here what we did, you are in C, the one that you have received is input is C, and the stack is empty. It means that this is the only thing that you have, and then you will be in Z0. Don't do nothing, don't do anything, go to Q1. So after this, what as I told you, at the end of every for example inputs, what we did, we have an empty symbol. So when you will be here at the end, if you are in Q1, okay, and you receive an empty symbol and the stack is empty, what you need to do is just move to another state and don't do anything. So this is Z0, and khalas, it will be what? It will be accepted. Now, so this is for the simple C. For example, it is ACA. So what I did, I will do this A Z0 inside the stack. This is Z0. Input is A. What you need to do is, as it is push, so this is for the push, we'll define a loop. Just keep A as it is, add A in the stack, okay, and then Z0 is already there. So it might be A, it might be B. Okay, as I told you, what we need to do in this case is that before C, whatever you have, either you have push or either you have A or B, you have to do a push. So let's assume what are the possibilities here is. For example, first of all, inside the stack, I have Z0. Now, in this case, what we will do, maybe you might push A, you might push B. So it will be Z0A, and this will be Z0, and you push B. Now, after this A, there are possibilities. Okay, the next element after this will be A, or the next element after this will be B. So if the next element, this will be Z0, previously it was A, the next element is also A. In here it is Z0, previous element is A, the next element is B. Same is the case here. Two possibilities. If the B is already there, the second element might be B, the second element might be A. So it means that it will be Z0 inside the stack. Previously it was B, the new element is also B. And here this is Z0, previously in the stack it is B, the new element is A. So now let's write the functions for this. So if for this one, we will write that what we did, I will not write the whole transition function, I will just write a part. In here, the element is A. Inside the stack, you have Z0, so it will be A, Z0. In here, for this one, that in the stack, the input is B. Inside the stack, it is Z0, so it will be B, Z0. Now for this one, now inside this, the input is A, inside the stack it is A. Okay, so it will be AA. For this one, it says that inside the stack it is A, input is B, stack is A. What you need to do is you need to do a push, which is BA. However, in this case, input is B, the stack top is B, you will do a push. In this case, here the input is A, the stack top was B, so it will be A, B. So it is 1, 2, 3, 4, 5, 6. So that's why if you see here, we have defined yani 6 push. 1, 2, 3, 1, 2, 3, 4, 5, and 6. Now, okay, so we did this here. What about that if we have something which is known as AC, yani A, because we might have something for we need a pop for the yani, for maybe more than one. Let's first yani see, for example, if you have we did this one for this one. Now if we have A C A, so how it will be executed, let's see. For ACA, first of all, I will do a push. I did a push. Then when it is C, what you did, so inside the stack Z0, okay, you have push A. Now the next element is C. So it means that what you did, you have input as C, inside the stack you have A. What you need to do is don't do anything. So this is for this. If it is B, C, B, so what you will be having inside the stack, it is Z0, here it is B. So if the input you receive is C, on the stack top it is B, don't do anything, keep B as it is. Okay, so here this is for yani, individual C, this is before C if it is A or if it is B. And then after that, what you need to do is, in this case, when you need to do a pop, yani if you can see here, this is A, B, it means that you will have a stacked Z0, you have A, you will have a B, then after C, whatever you will have here, if it matches the stack top, then do a pop. Okay, so that's why what I did, I wrote here as if it the input is B, on the stack top it is B, do a pop. Same is the case if the input is A, on the stack top it is A, do the pop, because it is a palindrome. So that's why you have seen here it is, and this thing is written. If it is same, then you have to do. If it is different, then it will be not a palindrome. And at the end, what you need to do, you need to write an acceptance, condition. This is about the palindrome, where it is very clear that what is basically the middle element. Now, let's consider another example. In this example, we don't know what is, yani we don't have the identifier. So it is WWR, yani this thing, 2 times A, okay, and yani 2 times B, it might be AB. So here we already know, yani this is basically the middle element. Let me first explain the push down automata, then I will tell you how computer know that this is basically the middle one. And as it is the even palindrome, so even empty is here allowed. So first of all, what I did, let's remove this one. Let's first solve it for this, and then we will do it for the empty. So here, what we in this case, what we need to do is we need to do the push, okay, and push A and B's, and when we get the middle, then we have to define the pop as well. So first of all, as based on those six things, here also we need to do 1, 2, 3, 4, 5, 6 push. Here, as we don't have any C, we don't have any state at here that will say no change. So here what we do we wrote the same thing which is related with the popping, that if it is A, for example, let's consider one of the string, and then we will see. Let's consider this particular string which is B A A B. In this case, first of all, this will be executed. Then we will have B. Okay, B is done. Now the stack top is B, and the new input is A. So this will be executed. After this, as we know, let's assume that we know how we know. I will explain it later. The next element is A. Okay, and we want to do a popping. So we will come here. As you see, the stack top is A, and the next element is A, do the pop. So from the stack, when this A is removed, we'll left with the B. So we will come here to this state, which is Q1, and here again, if the input is B and we know the stack top is B, what we did, this particular transition function will be executed, and at the end, what we have will have the acceptance state. Now, the question here is that how we know, or how the for us we can see the whole string, how the computer know that this is basically the middle. Let me explain you how basically it works. That's why we called it as non-deterministic. So how do it works? For example, if the string is B A A B, for sure for the first one it will do a push. So here in Z0 it will do a push for B. Okay, it will do a push. Now the next element is A. So if the top is B, okay, and the next element is A, so you can see we only have for this particular thing, when the top is B, when the input is A, just do a push. We have no other path for this. So what it will do, it will actually do a push, only one possibility. Now, when it comes to another A, if you can see, we have for this particular thing that if the stack top is A and the input is A, we have here one of the path, and we also have here another path. So that's why what the computer will do, it will actually run two possible paths. Here it will execute this, that we will be having Z0, this will be B, okay. So in one of the path, what it will do, let's assume it is running this thing. So it is A for another A, okay, for this particular A. It will do the insertion. However, for this one, Z0, B, this is basically here, BA, and what it did, it actually execute this one, okay. Now, when we came up with B, because for this one we are still in Q0, for this particular things we are in Q1. Now for this one, which is another B, okay, currently a stack top is A, okay, the input is B. What we did, we have here this path, only this path. So what it will do, it will go here Z0, then B, then A, okay. Then what we did, we have another A, and then again we did a B. However, in this case, when we are in Q1, so you can see we are in Q1, and the next input is what? The next input is B. So the next input is B, we are in Q1. So if the input is B, the stack top is B, what you need to do is you need to do a pop. Halas? So we did a pop. We are still in this case, we are in Q1. Now in this case, if you can see at the end, as I told you, of the every string, it is empty. So after this, what it will do, when it will, yani after doing, still we are basically in Q1. So sorry, Q0. So if it is empty, what will happen? We reach to the empty, symbol, but the problem is we didn't reach to the final state. So it means that that path is basically wrong. However, in this case, what we did, you can see we reached to an empty, okay, and there is a path. If we see this particular path, this path will lead us to the final state. So it means, yani, that this path is, and this path is the valid path, and in this case this thing is a palindrome. So this is the way how the computer can find out. It will define, yani it will follow all the possible paths, and then it will ultimately find out that either it's a palindrome or not. That is the reason why we, yani this one, PDAs are basically non deterministic, because for the same thing multiple paths are defined. It will execute all the possible paths, and then if even in one of the paths, if it reached to the acceptance state, then khalas, no need to check for the other paths. Now let's talk about the odd palindrome. In case of okay, now here we are still left with one part. So in order to support empty, what we did, we just define this path. Okay, you have only, because empty in the stack, still nothing, only z0, and you keep it as it is, and khalas, it is accepted as it is, even palindrome. Now let's talk about the odd palindrome. In case of odd palindrome, you have a word, and then it as it's a palindrome. In case of odd palindrome, it might be A, it might be B, it might be A B A, it might be B A B, and so on. So all these six are exactly the same thing that we did. This will be exactly the same thing. Here also this is exactly the same thing. Only we have some changes, yani here. So if you have only, for example, a single A, okay, what you need to do is, in that case, for example, single A, it means you have are here Z0. If you only have a single A, okay, what you need to do is, yani, for example, if you have this case, then you need to do a push. If you have, yani, a case which is only A, what you need to do is, don't do anything, just move to the next one. So this is for the single element, only for, yani, this one and this one, single A and single B. Okay, and for, okay, so these are this one, and then what you have when you have like A B A, in that case I will do push, I will ignore this one, and I will do a pop. And if it is, for example, B A B, so if you have, yani here I will do a push, A, as it is the middle element, I will ignore, and I will do a pop here. So you can see here what we did, that, okay, this is exactly the same thing like what we did previously. This is also same. This one is also same. Here, if you have A, B, A, okay, in that case, if if the input is A, stack top is B, then simply, yani, ignore. This is A, B, A. If the, in this case, if the stack, yani input is B, stack top is A, don't do anything, yani, sorry, here it will be B, okay, because if the input is B, stack top is A, keep A as it is. So you can see we have this one and we have this thing, okay, and this is, as I told you, for this one, for a single A and for a single B. Now, there are another possibility as well. Let's consider a case which is, yani, this one. It says that B, A, 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 B. So this is actually for the palindrome. Here, this is the middle, yani, element. So in this case, what we have, if the input is A, stack top is A, keep A as it is. Same is the case if in here, yani, instead of this, if it is A, 1, 2, 3 times B, and then A. So this is a part of reverse. This is the middle element. So if the stack top is B, input is B, stack top is B, keep B as it is. So because of this, we have yani this one and this one. So these four are for separating the, as a separator. This is for only a single element, and the remaining diagram is exactly the same thing. So if we can make a PDA that can support a palindrome, so I will have yani this one as well as the one that we wrote it for the even. So you can see here we have this one is from the odd part, this is the odd, and this is the even. However, this one, this and this is exactly the same for both the even as well as the odd. So these are the some of the example related with the transition diagram for the PDA. You know, the palindrome is, you can write the palindrome, for example, as we know that PDA is used in order to represent a context-free language. So for example, if we have a language which says that WWR, yani it is a palindrome where you have C as the middle, W is in the A plus B whole star. The context-free grammar is basically S A S A B S B, and here the PDA, if you would want to represent it in the PDA format with those 7 tuples. So Q is the set of states, which in order to make that diagram, Q0, we have Q0, Q1, and Q2. The inputs are A and B, okay? And inside this, we have A, B, as well as C we will be having, okay? And then we will be having also Z0 is something that is inside the stack. And this is the transition function we already know. This is the starting state, this is the final state, and inside the stack, the empty is represented by Z0. As I told you, in some of the book, they are using $sign. Somewhere maybe they use B, okay? Somewhere even they use such type of signs in order to represent this. So a deterministic and non-deterministic PDA. A deterministic PDA is the one in which every string has a unique canny path. But PDA by itself is always yani non-deterministic. A non-deterministic PDA is the one in which at certain time we have to choose among the possible paths. Now let's explore another topic, how we can convert a context-free grammar to the PDA. As we know that the PDA simulates the leftmost derivation of the word. As you can see here, what we did, these are the terminal, this is non-terminal, okay? So here, when you have the terminal on the left side, we call it as leftmost derivation. Here terminal is on the right side, rightmost. Here you can see we have both left and right, so we call it as a mixed. So here is the input, this is the PDA, either it will accept or it will reject. By using any helping, here we will be having a control unit as well as the stack, and ultimately here is the grammar. In order to simplify a context-free grammar, when we need to simplify a context-free grammar and to convert it into PDA, it must be first normalized. You can do the normalization by using Chomsky, and we can also use it by using Arabic normal form. A normal form is a specific format for the production. It allows the context-free language to be generated by a normal form. Why normal form? Because if it is in the normal form, it is easy to analyze, and it will be easy to generate a PDA. Okay. In the definition of context-free grammar, we didn't apply any restriction on the right hand side. The only restriction is on the left hand side. There will always be one non-terminal. If it is, for example, if it is not in the normal form, sometimes it will be hard to analyze. So that's why it is better in order to first convert it into the normal form. First of all, let's simplify context-free grammar by using some of the rules. For example, you need to do some useful substitution. If there are some useless production rules, remove that rule. Remove the lambda rule, but keep in mind not the lambda for the starting will be the same. However, for the other non-terminals, if it has lambda, you can remove yani lambda. You can have yani the unit productions, we might remove those unit production, and if there is any repeated rules, we will remove those repeated rules as well. Let's first consider our example number 1. Okay, in that case, if you can see, we have A implies X, B, Z, and B implies Y1. So here, yani B has only one possibility. So what I can do is I can simply, substitute, here instead of B, I will write Y1. So I can write that it is X, Y1, and Z. Let's consider this grammar. This is our example number 2. In this case, you can see A is equal to this, B is equal to this. So as this is the starting one, I cannot touch, remove anything from here. Let's do it here. Here, what we did, I will add the value of B. Now you can see here is that, okay, this is, I can't do anything. This is, I can't, however, B is here. Now let's see how we can solve this. You have A, B, B, small c. This B by itself, it can be either this, it can be either this, it can be, and the B value is A, B, B, A, and the B value is B. So here for this A, B, B, A, what we will be having, the outcome will be having this A, B replaces this B with this value. Okay, so this value is what? This value is yani A, B, B, A, and then we will be having our final yani C. And for this particular case, look, we already have this A, B. Instead of this B, replace it with this B, and then we will have our C here. So that's why we came up with this particular grammar. Let's consider an example of this one. Here, this is the starting one. Okay, here you will be having the value of X. Okay, here is the X. X can be A, X can be B, X can be empty. So look how we can solve this example. You can see we will be having an AX. Okay, so the X value, it can be either A, it can be either B, it can be empty. So it will be here AA for this particular path. Here it will be AB, here it will be only A. Okay, now for BX, as you know, X can be either A, X can be either B, X can be either empty. So for here it is BA, here it is BB, and if it is empty, it will be only B. So you can see here it is AA, AB, and A. And this part is BA, BB, and B. Here we did the substitution. Same is the case here. Here we can do the substitution. First of all, you can see we have two things. We have B as well as C. Let's first substitute the value of C in here and then substitute the value of B in this equation. It is easy. You can solve it by yourself. It's just a simple substitution. Same is the case here. You can see we have, I can't do any remove this one S. Okay, I have this A, I have this B. Okay, let's first solve one by one. Yani, as you see, what we have B is equal to this. So let's first, for example, add this value of B in here and in here. So you can see S will be equal to AB and S is also equal to AB by substituting this value of B. A will be the same thing, A, and in here it will be A implies AB because B is also here and here. That's why I cannot simply remove B. So it will be B, C, and the other thing is it will be A, B. Instead of this B, we will have here B and C. Okay, and then at the end you will substitute the value of this B value also in here. In here, and you will substitute this value of B here and here. Removing some useless productions. Let's see. In this grammar, if you can see, we have S is equal to ASB, epsilon, and S is equal to A. However, you can see A is equal to, so A is something that is like recursive, and it is something that is never ever ending. We cannot end a. So in that case, what we need to do is we need to remove this rule. If we will remove this rule, so if a is removed, a need to be removed from here as well. So this is basically your language. In here, if you can see, s is equal to a, s is equal to a is equal to c. Okay, a is equal to a, no problem. B is equal to a, no problem. However, c is something, okay, that will never ever end. So what we need to do is I need to remove c. When I will remove c, I need to remove c even from here as well. So I left with this grammar. So in this grammar, what we did, you have seen, we are not in s is the first one that will be executed. We are not using b anywhere, so we will remove b. Once you remove b, you left with here a is just one time a, so a will come here, and finally this is our grammar. We need to remove and empty transitions, null, those things, but make sure yani you can only remove if it does not belong from the start. If it is in the start, then you cannot remove that. So you can see any production, this is known as the null production. Any variable which is a, for which the derivation is called a nullable. So if you can see here, we have this particular language. In this language, s is equal to a, s, b, and epsilon. Now, for example, if I have what I did, instead of epsilon, okay, I just put the value here. So does this one and this one represent the same language? No. Why it does not represent the same language? Because of this language, even empty is allowed. However, here you can see empty is not allowed. So basically, the answer is that they are not same. In this case as well, what we did, we just put this epsilon value in here. Okay. So what we did, we have here a s, b s, and we put s as empty. Is it allowed? Is it equivalent? No. Because as per this, we can even have an empty language, but as per this one, an empty is not allowed. Same is the case here, that what we did, these are not same. So by after talking about this, after looking at this, we came to the rule that you can remove all the empty except the one that is for the starting symbol. In this case, as you can see, s is equal to as, and then also a, and a implies empty. So in that case, what you did, you can remove this one, and you can simply put it here as empty. So this is fine. This cannot make any changes in the language. Okay. So what you did, you put the value of here as empty. Removing nullable production. In this case, as these nullable production does not belong from the start, so what you can do is you can do those substitutions and then you can remove. So look, I have a, b, and c. If I need to remove this one and this one, what I can do is in here, okay, if a is null, I can only be left with bc. If b is null, I can only left with ac. If a and b both, if a and b both is null, I can left with c. So that's why you can see bc, ac, and c, and abc is here, because a is also equal to aa and b is also equal to b. And for example, if I need to apply it even, so what I did, AA, and then instead of here, I can write it as any, because here putting empty, I will left with A. Here for this B, putting empty, I left with B. So that's why you can see, first of all, you have put it here, and then putting these empty values in A, in this one and this one. Ultimately, at the end, you can see C implies C. You just need to put the value of C here, small c, putting small c, and remove this row, and so on. Elimination of unit production. Here also, what are the unit production? This is the unit production, which is c is equal to d, and this, and also this particular part is the unit production. After removing the unit production, you can put the values of this C, D, and A. You can see here that there are some useless productions as well. In the grammar, we are not using any D. We will remove D. In the grammar, we are not using any E. We will remove E and we'll just add the value of yani A in here and also C in here. Okay, with C is not used, for example, D and E is not used, we'll just remove. Okay, let's solve this grammar. In this case, you can see you have the unit production, which are basically S implies B and also B implies A. So first of all, you can see as this thing is as it is. Let's solve this particular B. Now you have seen B is either E equal to A or B is either E equal to BBA. So in this case, B is either E equal to A or B is either E equal to BBA. Now this A by itself is either E equal to BA and it is either E equal to BB. So that's why what we did, we already have this A, okay, and then we already have this one which we wrote it here. For this part, what we did, we have one value is BA, another value is BB, and another value is 3 times B. So because of adding those values of B, I have to remove this thing here. And then at the end, I came up with this grammar. If you want, you can further solve it in this A, writing the, for example, what you can do is you can just put the values of this A in this S in order to even solve it further. Removing the repeated productions, you can see here in this example, as these and these rules are repeated, halas, we don't need it. So we come up with this one. And you can further, if you want to solve it, you can just put the value of A here and you can just put the value of B here. Now the question is, why normal form? If all the production of the grammar could be expressed in the same format, then it will be very easy in order to design the algorithm, and it will be very easy to show the proof as well as the properties. Like in the regular grammar, we talk about union, intersection, concatenation, and all those things. And it also ensured the leftmost derivation. So two important normal form, one is known as Chomsky, another one is known as the Grabic normal form. So before converting to one of the normal form, we can eliminate all the 3 rules. What are the 3 rules? Let's see, it is written here. So a context-free grammar is in the Chomsky normal form if the rule is one of these format. A starting symbol, for example, if A is the starting symbol, so A implies epsilon. As we know that we only left epsilon for the starting symbol. For all the other symbols, we remove the epsilon. And a non-terminal, every time in all the grammar, if we want to convert it into the Chomsky, it will be S implies 2 non-terminal and S implies only one terminal, not more than one terminal. In case of Chomsky, it actually apply the rules on the right hand side, because in order for the context free grammar, when it's a simple context free grammar, what we did, we only apply the rule on the left hand side, having only one non-terminal. However, in the case of Chomsky, it is applying the rule on the right hand side. So it can be either this one or this one. Here B and C are non-terminal. Here A is basically a terminal. Let's see this particular grammar. If you can see, okay, 2 non-terminal, fine. Only one terminal here, one terminal here, one terminal. This is basically in the Chomsky normal form. Let's consider this example. In this case, because this is terminal, this is non-terminal. So that's why it is not in the Chomsky normal form. These two actually obeys the Chomsky normal form. However, this one does not. So that's why it is not in the Chomsky normal form. Let's assume if we have this one, this is okay according to Chomsky, this one, and this one. Khalas, the language is in the Chomsky normal form. Let's consider this example. In this case, yes, but however, here it is not in Chomsky because we have 3 non-terminal. However, we are only allowed to have two non-terminal. Even in here, we have two terminal, it should be only one. Now, if we want to convert the grammar into Chomsky normal form, how we can convert it? By using yani this way. Here, okay, this one is according to Chomsky, this one is according to Chomsky. Only the problem is because of this. So I need to replace this A's and B's with the non-terminal. So here what I will do, as yani S is already defined, I cannot yani touch anything with the S. Okay, because if I will put again S and S, it will be another, can be called again and again. However, what I did, I defined two other non-terminal. One is A and B, or you can call it as an X and Y. Okay, and replace this A with A and replace this B with B. Keep in mind, I cannot write here S implies SS, because S implies SS is different than S implies AS, because A is only equal to A. However, in case of S, it is applied to be yani repeated. So what we did, we now this is in Chomsky, this one, this one, this one, and this one. So this particular grammar is now in the Chomsky normal form. If you can see here, look at this example. This one and this one is as per Chomsky. The problem is in these two and also in this one. So let's yani solve it. In this case, first of all, what we need to do is, yani as I told you, as because this S is in the starting, I cannot write here in place of this as, for example, S, because S implies, this is basically not allowed. So what I need to do is I need to define a variable which implies A is equal to A, B is equal to B. So what we will do, I will convert this one as AA and this one as BP. So what I did, I introduced two variable non-terminal, and I just so as this one, all of these are basically so far in Chomsky. Only the problem is on this particular side. So here also I replace this with ASA and BSB. So the problem is now because of this. So let's propose two more variable, which is X and Y. Okay, for example, we will make X as, for example, SA and Y as SB. So what you did, you actually make one variable X, another variable Y. So now you can see all of these are according to the Chomsky. And here it will be S will be equal to ASB. And now again devise another variable which is X, make X is equal to SB, and here it will be AX. And now you can see your grammar is in the Chomsky normal form. Here consider this particular example as well. In this case, because of all these three, it is not in the Chomsky. So we have three variable here. It is A, it is B, and C. So we actually define, for example, U, V, and W as A, B, and C. So after doing this, instead of A, what we did, we write U. Here it is U, U, V. Here it is A and W. So this problem is solved. Only now the problem is on these two. So again, you will make an X, for example, as BU and Y as UV. And this language is now in the Chomsky normal form. You can see this example as well by yourself. These are some of the examples. Transform the grammar into the Chomsky normal form. These are some of the exercises. You can solve it, okay, by converting these things into the Chomsky normal form. So any context free, let's just do a quick overview. So any context free grammar may be generated by a context free language, can be generated by a context free grammar, and it can be converted into the Chomsky normal form. We'll make sure we'll eliminate all the rules with the epsilon, empty unit productions. Okay, but before doing it, that we can even normalize it and convert, any remaining rule of this one, and then after that you will convert it into the Chomsky. Simplified grammar, remove all useless eliminate empty, and even removal of the unit production.